And exam 4 is on Tuesday. And then I think you're turning your binders in on Thursday. Does that sound right? Any disagreements about that? Okay. So exam 4 is Tuesday. That would be the 17th, I think. And the topics will be everything up through internal loads. Remember, these are cumulative, so you need to be comfortable with the old stuff too. Every time I say that in statics, then I think like, okay, well, statics, that isn't such a big deal because so far every single thing in the class is built on everything before it. But remember that there can be old stuff. Internal loads.
Add these two vectors together.
Yeah. Any questions about the test? All right, well, today I want to just work on internal loads problems. First, I want to do one. I don't think it's been assigned yet. Is it number 6 or number 8? 6? Okay, so this one has 2 members that are connected to the floor by pin joints. And they cross. It looks something like that. Oh. They're connected by a pin joint. There's a pulley over on this one, and a cable goes from this one over the pulley and then back around the other direction, and it says that the force is 300 newtons. And then it doesn't give any dimensions at all. It has to, though, for you to solve it, so I'm going to give some. Let's say that this angle is 80 degrees, both of these. And the lengths of both of these are 1 meter. And that pin's at the midpoint. And we want to calculate the internal loads for each of these. Okay, so the first thing I'm going to do is, in a normal coordinate system like this, you know, what we would always do for structures, I'm going to calculate the external loads on both of those members. And then I'm going to talk about how to use rotation matrices to take our solution to the structure and get it ready to calculate the internal loads for both of those members. Okay, so I'm going to label these member 1. Wait. This one's member 1, this one's member 2. Okay, so, and then the joints A, B, C, D, E. And we're ignoring the weights on these. So I'm going to start with a free body diagram of member 1. At the pin, there's a force vector RA. At the pin in the middle connecting the two, there's a force vector F12. And then up at the top, the cable's connected to this one. And so the force is parallel to the body, away from the body. So this way. And since that's a cable that's path only goes over pulleys, the magnitude of that force is the same that it is anywhere else on the cable, so we know this is 300 newtons. I'm going to do this, go back to the table. I think, well, if you don't have vertical and horizontal members, I think it would be to try to do them just the way we do it with horizontal beams would be kind of a pain. Rho, force, moment. And then the about point, let's see, I guess I'm going to choose this. So first, the force RA. The rho vector is 0. The force is RAX, RAY. Cross product is 0. Then the force F12. This angle is 80 degrees. So, and the distance is 0.5 because the whole beam has a length of 1. So this is 0.5 times cosine and sine of 80 degrees, which is 0.087. And 0.492. Yes! And the force vector is F12x, F12y. Cross product is 0.087 F12y minus 0.492 F12x. And the 300 Newton force. The rho vector is just twice of this, so that's 0.174, 0.985. Force vector is negative 300, 0. So what's 0.985 times 300? 295.5. And then Newton's laws. RAX, RAY plus F12X, F12Y plus negative 300, 0 is equal to zeros. And the moment equation says, I'm going to rearrange these, negative 0.492 F12X plus 0.087 F12Y plus 295.5 is equal to 0. And so that's our first three equations. The first one says RAX plus F12X is equal to 300. The second one says RAY plus F12Y is equal to 0. And the third one says negative 0.492 F12X plus 0.087 F12Y is equal to negative 295.5. Any questions about the first body? And then the second body, the free body diagram, this is the one that's angled this way. Down here we have the force RB. At the connection we have the force negative F12. And then what's happening up here at the pulley? Probably not. Although if there's no friction, we have no way of knowing that. Two forces, yeah. Like you could think of, if you want to really make this clear to yourself, you could think of including the pulley as part of this body, you know. So there's the pulley. And you could also think of including the bit of the cable that goes around the pulley. And these are the little stumps of the cables coming off. And when you think about it that way now, those force vectors from the cable are pointing right out of those stumps. And it's the same cable, so that's 300 newtons for each of these. Yes? The height between them, I think we're going to find, that's a good question. I think we're going to find that, like, if I just call that R or something, that R is going to disappear in the answer. So let's try that. I think it doesn't matter. But obviously I lost some of my credibility when I didn't give any other measurements for anything else, you know. So rho, force, moment. First, the force RB. Put the about point down there. So rho vector is 0. The force is RBX, RBY. Cross product 0. And then negative F12. That rho vector is, you know, all of these are just going to be mirror images about the y-axis of the other one. So this is going to be negative 0.087, positive 0.492. And then the force vector is negative F12x, negative F12y. And the cross product is 0.087 F12y plus 0.492 F12x. And then the 300s, let's think of this as the lower one. I'm going to do them separate, but I think we're going to see that it disappears. The rho vector, so if that thing is located, okay, well, if we're thinking of that pulley, the top of that pulley at the top of that member, then that top one is going to be up. You know, that the rho vector, the top one is going to be what we had for the top before. So that's going to be negative 0.174, positive 0.985. This one is going to be 2 times the radius straight down. So that rho vector is going to be negative 0.174, and then positive, it is going to matter a little. Let's give it dimensions. Don't do this on the test. Well, if this happens on the test, make me give you dimensions and some extra points. Okay, so let's say that that diameter is 0.02 meters. Okay, so the vertical component of the row vector is 0.965, 985 minus 0.02. The force vector is 300, 0. And what's 0.965 times 300? Okay, so we got negative 289.5. And then the 300, the higher one, that row vector is negative 0.174, positive 0.985. Force vector is 300, 0. And this one is what we got before. Was that 295.5? If you just treated it as 1 right in the middle, they're going the same direction. And yeah, I think that is how it would work out. Yeah, it's going to behave exactly like it's right in between those two. Yep. Well, it's going. Yeah. You can move any force along its line of action. So, well, so I'm just going down.
You're accounting for the 0.02 in the line,
Mm-hmm.
but it's still, the radius still.
Let's draw it blown up. So if we have this pulley like this, and then the member goes up to the top there. The cable leaves right at the top of the pulley and right at the bottom of the pulley. And so that it doesn't leave, yeah. All this kind of stuff, though, I mean, you know, like if you have a problem like this and you have to get it right, it's important to think about, but I don't want to act like this is going to be some important thing for you to remember, you know. Okay, so Newton's second law says RBX, RBY plus negative F12X, negative F12Y plus, I'm going to add those two together, 600, 0 is equal to zeros. And then the moment equation says 0.492 F12X plus 0.087 F12Y, bless you, minus, so what do you get when you add those two? Minus 585 is equal to 0. And so those are our equations 4, 5, and 6. 4 says RBX minus F12X is equal to negative 600. Equation 5 says RBY minus F12Y is equal to 0. And 6 says 0.495 F12X plus 0.087 F12Y is equal to positive 585. And now we have 6 equations for 6 variables. What? Oh. Okay, 6 equations for 6 variables. So I'm going to set up a matrix. It has to have 6 rows and 7 columns. So equations 1, 2, 3, 4, 5, 6. And then the variables are RAX, RAY, F12X, F12Y, RBX, and RBY. And then this is the constant. Equation 1, we have 1 RAX, 1 F12X, 300. 1 RAX, 1 F12X, and the constant is positive 300. Then equation 2, we just have 1 RAY plus 1 F2Y is equal to 0. Equation 3, F12X, we have negative 0.492. F12Y, we have 0.087. And 295, negative 295.5. So F12X, we have negative 0.492. F12Y, we have positive 0.087. And the constant was negative 295.5. Is that what I said? Okay. And then equation 4. RBX, we have 1. F12X, we have negative 1. The constant is negative 600. Equation 5, RBY, we have 1. F12Y, we have negative 1. Constant 0. And equation 6, F12X, we have 0.492. F12Y, we have 0.087. And the constant is positive 585. Everything else is zeros. Okay. Anybody else get same thing? Good. All right. So now, there was some sort of tricky stuff with the structure. Hard to do structures without numbers, for example. But then dealing with the pulley is a little tricky. But now we have to take what we got from solving the structure and calculate the internal load. So let's start by drawing the two members out again with these loads on them. So member 1 is this one. Down here we have the force negative 594.8, negative 1663.8. Then at the middle, we have 894.8, 1663.8. And then up at the top, we have, it's 300 newtons going to the left. I'm going to write that as a vector because of the way that we're going to change the coordinate system here. So this is negative 300, 0 as a force vector. Isn't it pretty surprising? Like, look at this thing. It's like they're nearly horizontal. They have 80-degree angles. The only external, if we didn't have that cable there wouldn't be any loads on anything. We apply this set of horizontal forces, and we get these gigantic vertical loads. Isn't that kind of trippy? Yeah, but we didn't even include gravity. Yeah, that's weird. Okay, and then number 2. Down here we have the force RB, so that's 294.8, 1663.8. This is negative F12, so that's negative 894.8, positive 1663.8. It's negative, like I said. And then these, well, I'm going to just draw these like this because it'd get messy looking otherwise, but we have these 300 Newton forces like this. And these vectors are given in this coordinate system. We've never used anything else for structures, so that's what our answers are. But now, we're not used to doing internal loads with members that are up on an angle like that, We're used to, for internal loads, we want the beam horizontal and the coordinate system like this. Okay. So what we're going to do is use rotation matrices to represent each one of these force vectors in a coordinate system. So we're going to use a rotation matrix to re-express these force vectors in coordinate systems that have the x-axis pointing along the beams. So like, for example, for member 1, then we have this beam and a coordinate system like this. And once we've represented those force vectors in this coordinate system, what do we have to do to go from this situation to this one that we want? Just turn our heads a little, you know? Because all that matters to us mathematically is having the right relationship between the coordinate system and the member. Okay? So the rotation matrix that we want, we're going to do them one by one. But for member one, we want to start with this coordinate system and figure out a rotation matrix that takes us to so we have to figure out, yes?
One standard cosine theta, negative sine theta. Maybe I'm wrong on that, but one is there's like a standard way, and then there's a one where you do the transpose of that.
Oh, for the rotation matrix?
Yeah.
Yes. Okay. So I'll talk about the way that I recommend. I mean, really, either one is fine, but I recommend always doing it the same way. And since you're learning it from me, I guess I'm sort of passively recommending this one. But I'll talk about the difference between the two because it's, yeah, that can cause so many problems, you know? Yes. Well, they have to line up in the correct orientation with the beam. They don't have to line up with the coordinate axes. You could do it with unit vectors, but it's easier if t is in the direction of your x-axis and v is in the direction of your negative y-axis. It doesn't have to be, but it makes it easier. Okay, so first, to go from the coordinate system on the left to the one on the right, what's the counterclockwise rotation we have to make? 80, positive 80. So theta is equal to 80 degrees. And so the rotation matrix, capital Q, is cosine of 80, sine of 80, negative sine of 80, cosine of 80. And that is, cosine of 80 is 0.985. Sine of 80 is, I know I'm doing those backwards. Cosine of 80 is 174. Sine is 0.985. Negative sine is negative 0.985. And cosine is 0.174. And now we're just going to go one by one through these forces. So first I'll do the negative 594.8, negative 1663.8. Okay, so this rotation matrix, 0.174, 0.985, negative 0.985, positive 0.174, times the vector negative 594.8, negative 1663.8. Can someone, anybody fairly good at doing that multiplication? Positive 296.4? Okay. I think every TI calculator, if you can get these matrices, this matrix and vector entered in like this, it'll just do the multiplication for you. Yep. Mm-hmm. Yeah, it does have sort of a similar look. I don't really remember what you use a Ronskian for. Yeah. Uh-huh.
Differential equations.
Hmm. I'm sure it's based on some similar idea, but yeah. Uh-huh. Yeah, looks the same. And I'm sure it derives from something similar, yeah. And also, so the question that you asked, Eric, so sometimes, just because you're not confused enough when you do this stuff, you'll look in a textbook and it'll say the rotation matrix, the form of the rotation matrix is cosine of the angle, negative sine of the angle, sine of the angle, cosine of the angle, where these two are switched. The difference is there's two things that we could do. We could take vectors and rotate them, keeping the coordinate system the same, right? So, like this vector pointing that way, we could rotate that this way. We could rotate that vector 80 degrees, or we could rotate the coordinate system 80 degrees and keep the vector in the same direction. I think you should always use the same approach, because going back and forth between the two is going to screw you up 100% chance, you know. I always do the thing where I keep the vectors the same and rotate the coordinate system. But any job that you're trying to do, you can do either of those two ways. And the reason that the forms look so similar is, you know, if you have a vector pointing this direction, if you rotate the coordinate system up to that vector, that's, you know, say 60 degrees or 80 degrees or whatever. And to rotate the vector down is just the exact opposite rotation, negative 60 degrees. And that's why the form looks similar, but the signs of the trigonometric sign are backwards. So when you see it in my classes, I'm always going to be rotating the coordinate system and leaving the vector in its orientation.
Theta is negative or positive. It doesn't matter. Use the same formula.
Right. That's right. Okay, so the next vector we need is 894.8, 1663.8. Okay, so 894.8, positive 1663.8, multiplying that by the same matrix. And let me know when you get those. And then the last one, say it again. $295.5. Okay, and this is equal to that Q matrix, that same rotation matrix, times the vector negative 300, 0. So now what we have is, so now I'm going to rotate the beam, but remember that what we really did was rotate the coordinate. So I'm going to draw the beam horizontally just because that's what we're used to. But remember, mathematically, what we really did was the beam hasn't gone anywhere, and we just rotated the coordinate system. Okay, so now I'm going to draw it like this. We rotated the coordinate system to align this way with the beam. So that means that the force vectors that we transposed go in the order this, this, this. Okay. So when we do the rotation, on the left is going to be this. So that means over here, we have the force vector negative 1742.3, positive 296.4, and then in the middle, we have 1794.5, negative 591.9. And then at the end, we have negative 52.2, positive 295.5. And so now after all that, we have sort of an easy internal loads problem. So don't think about, that's what it looks like, that it rotated clockwise because I drew it like this. But really what happened was we rotated the coordinate system counterclockwise, then we turned our head a little. Okay? How many cuts do we have to make? 2 cuts. So cut 1 is for x values from 0 to 0.5. We have the force vector negative 1742.3, positive 296.4. And the internal loads T, V, and M. Newton's second law says negative 1742.3, 296.4, plus T, negative V, is equal to zeros. So T is equal to positive 1742.3. And V is equal to positive 296.4. And then the moment equation, neither of these two force components on the left produce a moment. So we just have M minus Vx is equal to 0. So M is equal to 296.4x. Yeah.
On our homework, are you going to assign this problem, or what should we do about that?
Why don't you use the dimensions that I used? Yeah, right. Maybe if I remember, if someone sends me an email, I'll remember. But if I remember, I'll update it on D2L. Yeah. And then the second cut, that's valid for x's between 0.5 and 1. So over here we have the force vector negative 1742.3, 296.4. And then somewhere else we have the force vector 1794.5, negative 591.9. And then the internal loads. So Newton's second law says negative 1742.3, positive 296.4, plus 1794.5, negative 591.9, plus t negative v is equal to zeros. And so what do you get for t? 52.2 negative. Thanks for the help. What? Oh. V? What's V? Okay. Positive 295.5. Negative, right? Yeah. For V?
Oh.
Okay, so we got those. And then the moment equation. We have a moment produced by, so that's a downward force of 591.9. Horizontal components don't produce moments. So we have a moment arm here of 0.5, a force magnitude of 591.9. That's a downward force, so that would be a clockwise moment. And then we have plus m minus Vx is equal to 0. So m is equal to Vx plus 295.5. And so m is equal to negative 295.5x plus 295.5. And if you graph this out, so here's the tension, shear force, bending moment. On the first half of the beam, we have a tension of positive 1742.3. And on the second half of the beam, we have negative 52.2. And then for the shear force on the first half, 296.4. And on the second half, 295.5. And then the bending moment on the first half, 296.4x from x equals 0 to x equals 0.5. So that goes to 148.2. So it'll go something like this. And then the second one, if you ignore round off error or whatever, it basically goes just like that. Where? Okay. Oh, okay. So you can do it either one of those two ways, and they give you the same answer if you're careful about it. And if you ever get confused, you can write out the row force moment table. Okay, so here's how I thought of it like this. Instead of being so there's two ways you can think about it. It's an upward vector with a value of negative 591. And in that case, you have a moment arm of 0.5 and a value of a negative force. So you get a negative thing. A vector going that direction makes it rotate counterclockwise, but you have the negative, so it's clockwise. Or the way I thought of it was, this is a downward force of 591. And so it's a moment arm of 0.5, a downward force makes it rotate clockwise. And, but man, like getting stuff like that straight with signs can be just so confusing. I actually yesterday in D form, like it was the worst I've got turned around in any lecture this semester. I like got to this sign thing and my signs were backwards, and that is always challenging. So if you ever get yourself turned around backwards, just scrap that way of thinking about it. Write out row, force, moment, and just do the calculations. Those are never wrong. Let's do the checks. So dm dx is negative 295.5. That's equal to v. dv dx is 0. There's no distributed load, so the derivative checks hold. And then we have horizontal and vertical point loads at both ends. So at x equals 0 and at x equals 1, we should have non-zero tension and non-zero shear force at both of those. And we do. And then the bending moment, since it's pin joints everywhere, there's no bending moments, no point moments, point couples at either end point. So the bending moment should be 0 at both ends, and that's what we get. So it all makes sense. And as far as damage, we would expect, there's more tension in the beam on the left half. The bending moment is getting bigger as you go close to the middle, so we'd expect as you get closer to the middle from the left half, that's where we'd be concerned about this thing breaking or bending or whatever. Any questions about that? Yeah.
I mean, where did you get the 148?
A 148. So I just looked at this function. So here's the function on the first half. M is equal to 296.4 times x. That's a linear function, so we know it's a line. And if you know it's a line, then you can just figure out what the values are at the two ends of that interval. So I plugged in x equals 0 to this function, and you get bending moment of 0 on the left. And when x is equal to 0.5 in the middle, you get 296.4 times 0.5 is 148.2. And so I drew a point at 0, a point at 148.2, and then just drew a line between them. On any of these where you have to use rotation matrices, the internal loads problems where you have to change the coordinate system, there can only be point forces on these. And that's because we haven't talked about what to do if you have a distributed load and you change the coordinate system. But it turns out that distributed loads are still vectors, and you can still use a rotation matrix. You just now end up with two components of a distributed load. One's horizontal. A horizontal distributed load doesn't produce any moment, so you're just dealing with forces. And then a vertical part, which is what you've dealt with up until now. If you spent some time, you could maybe figure out how to do it, but we're just not going to go into that. So the good news is once you get through all the rotations and stuff, the internal loads calculations are easy. Anybody have any homework questions, internal loads problems that you'd like me to go through or go through part of or something? Yeah. Yeah. Mm-hmm. Yeah, well, so these just tell you what, at any x value, this tells you what the internal load is. So if you wanted to know what the internal loads are at x equals 0.25, you look here and say that it's 1743 in tension, so it's being stretched at 1743. You go here, it's at 296 for that. You go here, and it's for half of that, 74. And so that's all those tell you. But if there's a place where all the values are at their maximums, then that's the place that you're most worried about. Yep. That's right. We've only done the one member, but let's skip the other one because it's basically the same thing. The only thing with the other one is you'd have to use a different rotation matrix. Okay, so with all of these, I don't think anybody would have chosen to have their x-axis pointing that way, just because, it looks more natural to think of this being the left end. But with this one, probably some of the class would do it each way. Your x-axis pointing that way, or your x-axis pointing that way. And you could do either one of those. If you did it like this, it would be 360 minus 80, so 280. Or you could just do it as negative 80. If you did it this way, it would be, yes, so 100. Yep, exactly. And your functions would look different, like the coefficients on things would all be different. But they would all, if you use those different functions to represent the same physical point, they would tell you the same thing. So either one, they're equivalent, but they look different. Yep.
This might be a question. I'm just thinking about it. So the pulley, if it's the same width as like the bar that it's on, didn't we do something earlier semester where you can like move what the point is? So couldn't you sit it over like the point forces? So if it was the same width as the thing, to make your row column easier, couldn't you sit like move that point where the tension was?
Yeah, so you can move the horizontal point anywhere you want in that case, because you can move it along the line of action. That's what you're talking about. Yeah, I'm not sure it would have made it. I mean, yes, you're right, you can do that. But since these forces are horizontal, you can move the x position, but you still have to figure out the y position. So that's what that's what we had to do anyways. So it didn't help us with that. Yeah, right. Any other questions? Did you have a homework question? What's the first answer? I don't know. It looks hard. Did you have a homework question? I thought you were looking for one. Anybody have the homework? Oh, that's one of the ones that we were talking about, right? Okay, good. Number 4, cut 1. Okay, so internal loads number 4. We have a fixed joint on the right. That means we can get away without calculating the external load, so that's good. And then we have a distributed load just on 1/2. And I think this is the one where, for some reason in my solution, I did it as if this thing has a mass of 400 kilograms. I don't know if I changed the problem later and didn't change the solution, but let's do it the way it's written here. Okay, but if you did it and then compared the solution and there was like one distributed load and you didn't know where it came from, that's what it is. It's dealing with the mass of this being 400 kilograms. Okay, so 6,000 newtons per meter. This distance is 1.2. This is 1.2. The cuts are going to be at the end, well, these important spots where the functions change at the ends, and then the distributed load function changes there. On this first half, so cut 1 is for x between 0 and 1.2. And on this one, what's the function q of x? 6,000, yep. It's just a constant function. No matter what the x value is, the height of the distributed load is 6,000, so that's it. And so when we take the vdx, we should get negative 6,000. Okay, so the first cut, the right end is somewhere inside that distributed load. The height 6,000. The width of the piece is x. And then T, V, M. And now to treat that distributed load as a point force, the area of that rectangle is 6,000x. The centroid's right in the middle. And so Newton's second law says 0, negative 6,000x plus T, negative V is equal to zeros. So there's no tension. And the shear force is negative 6,000x. And then the moment equation, the moment arm of that 6,000x force is x over 2. The force is 6,000x, and that would cause a clockwise rotation around the left end, so that's negative. Then plus m minus vx is equal to 0. So m is equal to vx plus 3,000 x squared. And so m is equal to negative 6,000x squared plus 3,000x squared, or negative 3,000x squared. dm dx is equal to v. Negative dv dx is equal to q, so those all work. And then the second cut, I'm going to do the second cut too. So you're dealing with x values from 1.2 to 2.4. So now the right end is not inside that distributed load. The distributed load has this height of 6,000. The distance from the left end to the end of the distributed load is fixed now. That doesn't depend on x anymore. That's just a distance of 1.2. And then you have the distributed, internal load P, V, M. This distance is x. So Newton's, so now we can represent that rectangular load as a point force. The area of that rectangular load, since we have a fixed length, is just 6,000 times 1.2, which is 7,200. And it's at a location at the midpoint of this 1.2, so this is just 0.6, the magnitude 7,200. And then you have these. And once you do that, then the calculation's easy. Any questions about that?